Okay. Now, the action potential is not just, an issue of the voltage-gated sodium channel opening, right? Because if you think about it, if you were to depolarize to -55, you open up the sodium channel, it's open for 1 millisecond, it's open very quickly, shuts, right? During that 1 millisecond, you have all this sodium rushing in. You're going to make it very positive on the inside. I suggested it's up to positive 20, right, millivolts inside versus the outside. But how are you going to get back, right, to the resting potential? I mean, you're not just going to have the sodium in this very, high, or very, positive internal state. You actually have to return at some stage to the resting potential to reset all of those sodium channels, for example, and allow for another action potential to begin. So it turns out that the sodium channel will open at -55 very rapidly and then close, right? There's another voltage-gated channel. And again, this just means a channel that is gated, closed, or ungated, open, depending on the voltage, right? Depending on the difference in charge across the membrane. This is a voltage-gated potassium channel, right? And this one is closed also at the resting potential. At the resting potential, the -65 inside versus the out, the pull of positive and negative charges will have it in a specific shape in which there is no channel, right, that allows for the passage of potassium. But at -55, around the same threshold value as the voltage-gated sodium channel, it starts to open. Okay, it opens a little more slowly, but even more importantly, potassium initially will leave a little more slowly, and then will start to accelerate its rate of exit from the cell. Now think again. Why is it leaving the cell, right? Remember that you find potassium at high concentration inside the cell and low concentration outside the cell because of the operation of that sodium-potassium pump, right? So the concentration gradient force will drive it out. At -65, remember we have a few open potassium channels, right? And it flows out, right? So it will leave. It'll come back in via the pump, of course. But even though it's negative on the inside and it's a positive ion, the concentration gradient force sort of wins out, right? And it seems the general direction of flow is out to the extracellular space. So initially you open, at the same time you're opening all these voltage-gated sodium channels, the sodium is going to start to rush in. You're also opening these voltage-gated potassium channels, and the potassium is going to start to flow out. But it will accelerate its rate of outflow pretty quickly, because as you bring in all this sodium, see all this sodium that's actually now shown here in this image, you make the inside briefly positive relative to the outside. Remember, with all that sodium coming in, you're further depolarizing this, this membrane, and all of a sudden, not only is the concentration gradient force driving potassium out of the cell, but all of a sudden you've also got the electrical force driving it out, right? You've got all these positively charged ions in here, which are going to repel potassium and send it out. So the rate of potassium outflow will change as the what's called action potential continues, right? You have all this sodium coming in at -55 through these voltage-gated sodium channels. They're just open briefly for a millisecond. And then these potassium channels that are opening, initially there'll be kind of a slower outflow, and then it'll rapidly increase as you further depolarize the inside of the cell by the entry of sodium.